Oh, fantastic. This is even better. Let's use this. Hello. Yes. Okay, come on over. Bijective lenses. Let's get the ball rolling. So this is lightning, so this is going to be really quick. You have 1 minute on this.
Great. So I know if you've ever worked with Linux configuration files, especially programmatically, you know that they are not very fun to work with. Especially programmatically, our tool is built to kind of make that sort of thing easier using synthesis. We let people put in regular expressions describing data formats. So maybe you could have one format which is a Linux configuration file and one format which is a principled format like JSON, and we automatically synthesize converters between the two using this language of lenses. You can see an example one in blue at the bottom. So we're going to make that easier. Hopefully it'll be a fun talk. String section. See you there.
Okay, thank you very much. Just hit next.
Have you ever had to do a boring, repetitive task on the web and wondered it would be nice to have a tool that can automate this process? Well, WebRelate is going to solve this problem for you if you want to get data from the web to populate some columns in your spreadsheet. And with WebRelate, you just have to provide one example for most of the tasks, and the system would automatically learn a program to do this for the remaining rows in your spreadsheet in just a few seconds. So if you're interested in knowing more about this, please come to our talk. It's the second talk in the next session. Thank you.
Thank you. Next. Anthony.
All right. Okay, so strings are fundamental data type in most programming languages, but their generic nature can, but their generic nature can cause a lot of subtle programming errors, some with serious security vulnerabilities like cross-site scripting. One vision of research assistant constraint solving is to come up with a rich constraint language and a solver for the language, which can cater to analysis of string manipulating programs. In this paper, we laid down the foundation of algorithmic foundation of string solving with for expressive constraints that include replace all function. And the replace all function, what is it? Well, an example is if I want to replace every occurrence of eat in I eat meat by slice, you get I slice, M slice. And if you attend the full talk, I will tell you a little bit more why this is especially important in the context of cross-site scripting vulnerabilities.
Okay, thank you. And Andrew is special. Anthony is special. He has 2 talks in this session, and he's going to tell us about the next one.
Okay, so the next one. So finite transducers are an expressive and widely used formalisms for modeling string functions, especially for cross-scripting vulnerability analysis. For example, HTML escape, which converts certain reserved of meta characters to this corresponding HTML codes. So, for example, this is one such example, and it's also can be used to express certain aspect of replace all function. In this paper, we provide the first practical algorithm and solver for string constraints with both concatenation and transducers as primitive operations. Even though it's undecidable in general, the constraint language, we provide a completeness guarantee for an expressive symbolic execution analysis fragment. And there are 2 crucial ideas here. One is the succinct alternating automata for representing symbolic representations of solution set. And finally, the fast hardware verification algorithms like IC3 for finding solutions. Thank you.
Thank you, Anthony. Yeah, Arno? Here you go.
Okay. Say I want to reason about resources, whether a file has been closed, whether a socket is listening for a connection, whether a memory location has been initialized, this sort of things. Computer scientists have known for a long time where to look for this sort of things. It is in the vicinity of linear logic. Unfortunately, these turned out to be a bumpier road than expected, and there are very few programming languages that actually leverage a type discipline like linear logic. And the reason for that is that linear typing tends to be intrusive. It tends to overhaul the entire programming language design. And what we show in the paper is that this need not be the case, that you can extend your favorite programming language with linear types in a lightweight way. And despite the title, it doesn't need to be Haskell. It's whatever you like. But we do use Haskell and GHC as our example.
Thank you. Who's next? Madhu, your slide caused a problem. There you go. You want to start?
Okay, so this talk will be on foundations of heuristics called natural proofs and quantified instantiation. So this is really heuristics that are used to automate logical reasoning. And the question is, why do they work well, and especially natural proofs, why do they work well? And we develop theory to explain why they work well. We look at logics, several logics, first-order logic with least fixed points and background theories, and identify logics for which these heuristics are actually complete, and explain why natural proofs, the setting they are in, actually show they're complete. And also, when they're not complete, we bridge them using, we bridge the incompleteness using automated lemmas that are synthesized. And we also point out some mistakes in earlier work and some open problems.
Thank you. Who's next? Luke Kong, Steve Ram. Oh, Steve.
Thanks. So this is joint work with Toby Cathcart-Byrne and Luke Ong from the University of Oxford. Constrained horn clauses are a class of formulas in first-order logic that have become important in automated program verification. They become important because, well, one reason is that they give a purely logical treatment of first-order program invariants. Now, when we want to verify higher-order programs, we often want to talk about functions directly in our invariants. So higher-order logic is often a better choice than first-order logic. The starting point for this work is a natural generalization of this constrained horn class into higher-order logic. And later on, I'll be talking about the existence of canonical models in this class and also how to do satisfiability solving using refinement types.
Hiroshi.
Well, this talk will be about verification of high-order and non-deterministic programs. We propose a novel dependent refinement types that can express and verify both universal and existential branching properties of programs. And our system can seamlessly combine universal and existential reasoning. And for example, we can prove non-safety via termination and non-termination via safety. We have also studied meta-theoretic properties of the type system, such as soundness and relative completeness, and we also show that types are closed under complement in our system.
Thank you. Antoine, who's this?
Thank you. So in our paper, we talk about using quasi-quos to do meta-programming. And in particular, we show how to statically type analytic quasi-quotes, which are quasi-quotes that can inspect program fragments as well as construct them and compose them together. And the way this is done is by reflecting the type of the program fragment and its context requirements in the type of the quoted program fragment, which enables also interesting program transformation rewritings, program transformation primitives that allow you to have well-typed, type-preserving rewritings. So we formalized our approach and we implemented it in Scala without modifying the compiler, and it's available online.
Oops. Thank you. I think next is Jens. There you go.
So we want our partial evaluator to optimize a lot. And the best we can hope for is Jones optimality, which we have from Neil Jones. And Jones optimality is something that's been hard to get in the past. And in my talk, I'm going to try to persuade you that we can design and implement a partial evaluator that is Jones optimal and is self-applicable and is statically typed. And the new concept we have is called specialization safe normalization. I'm going to define that, and then I'm going to go over how to type check the new partial evaluator. And I have experiments with 3 different kinds of representations and 3 different programming language semantics. And I'll make sense out of that graph. You can see never a slowdown.
Peter.
So traditionally, static and dynamic typing have different strengths and disadvantages, and gradual typing has emerged as a way to try and get the benefits of both static and dynamic typing and the drawbacks of neither. And an important thing is that for a program, we now have a spectrum of types, so we can alter type annotations and move our type from dynamic to static or static to dynamic. Unfortunately, these migrations can be quite difficult. As we change type annotations, we run into type errors, and trying to manually migrate these programs can be trying to push a car that's stuck in the mud. So we've developed a system, migrational typing, which can automate this process so that you can migrate to type-safe programs much easier and automatically.
Thank you, Peter. Who's next? Aryan?
Thank you. So I can spoil the answer to this question. It will be yes. But the why and the how are also really interesting. And if you want to know how we creatively use dependent types in this context, then you should really come see this talk, which is in the block after lunch. Last one.
Thank you. Who's next? Whoa. Simplifying ARM concurrency.
After 10 years of work and various POPL papers proposing complicated concurrency models for Power and ARM, we can now report things are getting simpler again in the case of ARM. Partly as a result of our previous modeling efforts, ARM have shifted to a much simplified concurrency architecture, and for the first time have a formal official concurrency model as part of the architecture documentation. I'll present this this official axiomatic concurrency model, a simplified operational model, handproof of equivalence between these two, and a testing and debugging tool built on top of the operational model. Our talk is called Simplifying ARM Concurrency, Multi-Copy Atomic, Axiomatic, and Operational Models for ARM v8, in joint work with Shaket Floor, Will Deacon, John French, Sasmit Sakar, and Peter Sewell, where Will Deacon has been working on this from ARM. At 1640, track 1.
Thank you. Let's see which one was next. There you go.
Hey, the talk is about specifying and reasoning about implementation of locks. Also, in general, objects with partial methods. We probably all think we understand locks very well, but if we consider progress properties, there have been so many progress properties proposed for concurrent objects, but surprisingly, none of them applies to locks, including this lock freedom, wait freedom, starvation freedom, and dialog freedom. Also, there are no so-called progress-aware abstractions, which allow us to achieve contextual refinement, which are important to achieve compositional progress verification. So we try to answer all these questions in our talk and also in our paper. Please come to our talk. Thanks.
Thank you. Who's next? William? No, Thomas.
So what we're doing is that we are considering the problem of refactoring in ML. So we often happen to write some data type like in blue and some function on this data type. And then when we want to do one little change in this type, we have to find every place where something needs to be changed and fix it. So we are considering another approach. We use something called ornaments to describe a class of transformations on data types and try to do automatic lifting of functions from the original type to the new type. We actually proceed in a principled way. So instead of just doing some random transformation, we generalize the type and then to work on many variants and then specialize it. And we have an implementation that does this as a prototype. Thank you.
Thank you. And I think it's William next. Yeah.
Hello, everyone. So later today, I'll be talking about type-preserving CPS translation of the calculus constructions with sigma types. So this is part of a longer-term project on how to write not only a verified compiler for Coq, but a type-preserving compiler for Coq. Now, the reason we care about type preservation is that when we write a verified program in Coq, we spend a lot of effort encoding our program invariants in our types. And if the first thing our compiler does is throw out those invariants, then we can no longer use type checking to enforce our invariants when linking with unknown code. So our long-term vision is to compile Coq down to some sort of dependently typed assembly language then use preserving all the typing structure all the way down, then use type checking to automatically enforce our invariants, our safety and security invariants when linking with unknown code. So the CPS translation is the first part of such a compiler and is in many ways the hardest part, because about 15 years ago, with some caveats, it was proven that type preserving CPS is impossible once we have sigma types. So if you want to know how we exploit the caveats in that result and how we develop this translation, come see my talk later today. Thank you.
Okay, and our last lightning speaker is Nikolai. Oh, Andre, sorry.
Yeah, this is. I thought my talk was about categories, but apparently it's on safety and conservativity. But maybe let's see. Okay, so I will have no slides. Hopefully I will have slides later today. My talk is in the last session. And yeah, so I will talk about categories in dependent type theory, especially in homotopy type theory. And I will try to explain why ordinary categories are not always enough. What we really want are higher categories. And higher categories are somewhat challenging. But I will try to present a possible definition for higher univalent categories. We call them complete semi-Siegel types because they are combining the idea of Siegel spaces of Charles Resk and the completeness, which is a very simple trick and which can be formulated in our setting, which is due to Lurie and Harpers. And yeah, it's joint work with Paolo Capriotti. Thank you.
Okay, well, thank you, everyone. So let's break for coffee, and then after that at 10:30 it splits into 2 parallel tracks.